What we ended with then is right here at example 2 on page 20. This vector field is a conservative vector field. We went through and checked, kind of like Russell was asking about in the homework, if we think about 1/2 xy being a partial respect to x and 1/4 x squared being a partial respect to y, we can use that to make sure this is conservative, which indeed it was, and that's why the path didn't really matter. When we have conservative vector fields, they've kind of got two things now that are good for them. One is what we already knew, is if it's conservative, we can find a potential function. And now the other thing is going to be if it's conservative, we really don't care what path we're traveling as we go through there. We're going to get the same value out no matter what. And that leads us to this guy. And this makes some of these problems a whole lot easier. So we have the fundamental theorem of calculus. This is the fundamental theorem of line integrals. It's very, very similar. What it says is if we have a conservative vector field, the way we can evaluate the line integral is sure we do the things we did before, but a much faster way to go through and do it is to find a potential function and then basically do the fundamental theorem of calculus on the potential function there. So we do have to first go through and check and make sure it's conservative. We have to make sure that that happens. But as long as it's conservative, then we say, okay, well, what's the potential function? Like it says here, where f is potential function, and we're going to go back and evaluate that potential function at the end point, and then minus that potential function evaluated at the beginning point. That's it. It's a much simpler way to go through evaluate these.
That answered my question on the last question.
Oh, really?
This was the last question.
Okay. The homework went over 15.3? Maybe it was kind of leading to this.
Yeah, the last question I just remember the integral. Oh, yeah, FDR.
Hello. What's going on?
Are you guys in the middle of class? Oh, I'm sorry. I thought you were in between class.
No.
I'm sorry. I thought I'd get you in between. Sorry.
That's good. All right. So to reword this, I mean, I kind of just said there, as long as we have a conservative vector field, we're going to go through and find the potential function and then essentially do the fundamental theorem calculus on that. But basically what this means is we don't care about what the path is. So for a conservative vector field, which is very important, we have to have that conservative vector field piece. If it's not conservative, it doesn't work out. For a conservative vector field, the path doesn't really matter. The path we travel through it does not really affect the line integral. We just need to know where we start and where we're going to. Okay, that's really all we need to know is where are we starting at and where are we going to. It's a conservative vector field. Whether we go a really long, windy way through it or a straight path through it, it's going to go to the same answer. So this kind of gives a bypass for all of the parameterization that we were doing before. I mean, we're not going to parameterize this. We're just going to test if it's conservative and go through and find the fundamental or find the potential function. So here we go. Example 3. Evaluate the line integral where C is a piecewise smooth curve from -1,4 to 1,2, given by that picture. And there is what the vector field is. Okay. Now, obviously, this one's going to be conservative because the example we just did, but ignore that thing for a minute here. If we didn't know conservative vector fields had this nice little shortcut to it, we'd have to go through and find a parametric equation for this line. How would we even start doing that? Does this curve look like a function you can name easily? It's not linear. It's definitely not a parabola. It's not a sine. It isn't even really a function technically. I mean, it fails the vertical line test over here. So this would be an incredibly difficult problem if this thing isn't conservative. Okay, because that is a very difficult curve to try to parameterize here. So we can start to hopefully see the benefit of this. But again, the first thing we have to go through and do and check and see if it's conservative. And even though, like I said, we just had an example, this one is going to be, I want to make sure you guys go back and check that. So like we saw on the homework, if this is a conservative vector field, this is the gradient of something. So we're saying this is the partial with respect to x, and we're saying this would be the partial with respect to y. And so if the second partials, if the second mixed partials are equal, we know it's conservative. So we're going to go back and do that. We're going to find the partial of m with respect to y. And then we're going to go through and find the partial of n with respect to x. We're essentially just finding these second order partial derivatives.
Why is it that the m is related to the y first And then the n is related to the x.
Because if this here is a gradient, what is a gradient? I'll go back to answer that question. What is a gradient? What is that? How do we find it?
Is it the partials?
It's a partial respect to x and partial respect to y.
Right.
So if this vector field is a gradient, then 2xy is the partial respect to x, correct?
Right.
So what we're saying is, okay, if that's the partial respect to x, and the other guy n is the partial respect to y, when you think way back to when we learned about partial derivatives, one thing we said was the second order partial derivatives for the mixed partials are the same. So basically we said that this was equal to this. Remember doing that?
Yeah.
Okay, and that's what we're going back and using here. If this is already the partial respect to x, we just now take the partial of that respect to y. And that's why we go back and have that y down here in the denominator.
All right.
And then similarly for the other guy. If that's already the partial respect to y, we need to find the second partial respect to x. So that's why we have x in the denominator for n. Does that get to your question?
Yeah, gonna make sense.
Okay. All right, so partial of m with respect to y is 2x. Partial of n with respect to x is also 2x. And yay, they're equal, which means it is conservative. If this was not conservative, we would not finish this problem. I'll just tell you guys that now, because that is not a function I could parameterize without some software. But since it is, the next thing we can go through and do is find a potential function. And this goes back to the homework that was just due last night, is we're going to now say, okay, we know for sure that 2xy is indeed the partial respect to x. So we want to undo that differentiation. We're going to go back and say, okay, now we need to take the antiderivative of m with respect to x, because we want to take that partial and get rid of that differentiation that we did. So antiderivative of xy dx. And what does that give us? X squared y plus some constant. Similarly for n, we verified that yes, that's a gradient, which means x squared minus y is indeed the partial derivative with respect to y. So we need to undo that differentiation.
That is going to be
Which is what? X squared y minus 1/2 y squared. Which means what is our potential function?
x squared minus 1/2 y squared plus c.
X squared y minus 1/2 y squared.
And then basically we're just going to say, okay, there's my function. I've got that antiderivative. We're just going to go back and plug in the beginning point and the end point. So we're going to apply the fundamental theorem of calculus, which I didn't spend a lot of time explaining, but that's really all it says here. We have some line integral. We're going to go through and to evaluate that line integral, kind of think about skipping this middle step here. We don't really care about that. We're going to go through and find that potential function, evaluate it at b at the end point minus the values you get from a at the beginning point. So what that looks like in an actual problem then. So here is my beginning point. These are going to be the a values. Here's my end point b. We do have to go back and plug that into the potential function. So let's write it this way. So for our actual value of the line integral, we're going to have the potential function, let's write it out actually, x squared y minus 1/2 y squared. The plus c really doesn't matter. I mean, think back to doing fundamental calculus. When you go through and take the function minus the function, the c's cancel out. So we're just going to go ahead and skip that. If you want to write plus c, it's just going to cancel out. That's fine. But we're going to go back and evaluate this from the initial point, which is the lower limit. So that's -1, 4. And then to the upper point, the end point. And then just keep in mind it's an ordered pair. So we're going to let x equal 1, y equal 2. That potential function for that. And let x equal -1, y equal 4, and evaluate the potential function for that. So let me color code this. All right, so we get 1 squared times 2 minus 1/2 times 2 squared. That's the end point, so we always do the bigger, the last point first. And then we're going to subtract the initial point. So that would be -1 squared times 4 minus 1/2 times 4 squared. Oh, we get 1 squared is 1 times 2 is 2. 2 squared is 4 times 1/2 is 2. That gives us 1 times 4. 4 squared is times 1/2. So 0 minus -4, or just positive. And that's it. No parameterization, no t's. We just have to work with this. I mean, it's a little awkward because we're going back and plugging in x's and y's, but if you try to remember, it's just like the fundamental calculus, it's just a more complicated problem. It's still easier to do it this way than it would be to try to parameterize this. Questions on where things came from or what we did there? We'll work another example. Not just say, yay, we're done. You guys got it. But again, the process is if you're given any line integral now from now on, anytime you're given a line integral, check to see if it's conservative first. Okay, that wasn't really important before because it didn't change anything, but now it can definitely change things. Always check to see if it's conservative. If it is conservative, we're going to go through this process. If it's not conservative, we're still stuck on what we did before. We still have to go through and parameterize it and do all that stuff there and write it in terms of t, and it's a much more involved process. All right, example 4, page 22. Evaluate the line integral where C is a piecewise smooth curve from that point to that point, and now we are traveling through space. So again, same idea is that's going to be a very complicated curve to parameterize, probably going to be a conservative vector field, but we still want to go back and check it. When we are working with space, not just a plane, so if we have 3 dimensions, how do we go through and check and see if it's conservative? Yeah, we look at the curl, okay? And there are some other ways you can think about it. Basically, we want to check and see if the curl is 0 on this one. And I don't remember exactly what page that was on. Oh, there it is. That's a very colorful example there. So back on page 8, we had our test for 3-dimensional conservative vector field. And yes, it is just checking to see if the curl equals 0, but we went through and said that would be the same thing as checking these 3 conditions. So whatever way you want to approach it, if you want to full on find the curl, that's fine. But I'm just going to go ahead and do this little alternate way here. So page 8 is where this next section is coming from.
But to find the curl, that's when we set up the whole entire matrix, right?
Yep. So yeah, when we did the curl, go back to this. This is how we defined the curl back on page 7. It was that determinant. Go down a little bit here, this whole thing here. But what worked out was if the curl was 0, we know that this term has to be 0, and this term has to be 0, and this term has to be 0. So another way to go through and do it is instead of going through this whole process is just find each of those right partial derivatives and then just check to see if they're equal to each
No,
other.
I get that. I'm just wondering, like, as far as the test goes, like, are you going to be asking just to find the curl on the problem, or is it going to be like?
Yeah,
this,
on
where
a
it's
problem, I
just-
mean, I could. I don't know exactly what I'll put on the quiz this time, but theoretically, yes, I could say find the curl of this vector field, and then you have to go through this whole process here. Yes. Yes. Okay. All right, so let's check this though. And I don't ever remember I will do this. Yay for note cards. Okay, so we need partial of p with respect to y. We want to see if that is equal to partial of n with respect to z. So let's see if that happens. What is the partial derivative of p with respect to y? 2z. And then the partial of n with respect to z is also 2z. That's what we wanted. Then we're checking the partial of p with respect to x. And see if that equals a partial of m with respect to z. So p with respect to x is 0. And m with respect to z is also 0, so good. So far, so good. And the last pair we want to check is partial of n with respect to x and the partial of m with respect to y. So n with respect to x is 2x, and m with respect to y is also 2x, so we're good. And again, if you want to find the full-on curl, that's fine. That'd be a-okay to go through and find the determinant of that matrix. Just if you have your little things in your note card, that's probably a little faster. So what this tells us is it is a conservative vector field. And again, if it wasn't conservative, we would not be doing this problem right now because there's no way we're going to go through and parameterize out the information that we're given right now. So this is really kind of the only way we have to go about this. So now we need the potential function. Essentially, we've said, yes, this is a gradient of something, so undo that partial differentiation process. We're going to find the antiderivative of the x with respect to x, y respect to y, and z respect to z. So antiderivative of 2xy dx, antiderivative of x squared plus z squared with respect to y, and the antiderivative of 2yz with respect to z. So this guy gives us x squared y plus some constant. Second one gives us x squared y plus z squared y plus a constant. And the last one gives us z squared y plus a constant. So really this middle section right here, that is our potential function. Okay, that's got all the pieces. Got the x squared y, the z squared y, just combine into one. And then what do I do with that information? Yep, plug in the endpoint minus initial point. So we're going to take the potential function at 0, 2, 3 minus the potential function at 1, 1, 0. So 0 squared times 2 plus 3 squared times 2 minus 1 squared times 1 plus 0 squared times 1. So looks like we get 18 minus 1 or just 17. Kind of felt like I rushed through that one, but do you guys have questions? Again, if it's conservative, find the potential function, which we've talked about doing before. And now what we're going to do with that is, okay, well, from the potential function, we're going to do terminal point minus initial point, kind of like we do for, I don't know, let's just lots of times. And while you guys are finishing writing that down, I can just use this. If we were going to do that example we just did using the old methods, so going back and parameterizing, we need to have something that tried to parameterize this curve. This vector I give you here for R is not this curve. It's just a different line that would go from point to point. Because if you think back to this example here, we basically said that it didn't matter which path we were on for that first example, we always got the same answer. So the idea is if we just pick a simple path and go through and do this the way we did before, and we can write out the integral, what we'd have to go back and solve is from 0 to 1. That would be what t is parameterized as. We'd have this vector field, so 2 times x times y, which is 2 times 1 minus t times 1 plus t. This is all going to have to be dot product. And then the next guy would give us this eventually, 1 minus t squared plus 3t squared. And then 2. And that would just be rewriting the vector field f using the new x and y and z. We still have to take the dot product of that with the derivative of x and y and z, which is negative 1, 1, 3. And then we do go through and integrate that. And that's totally doable. I mean, if you did this, you should get the same exact answer we got. You should work through this, you should get 17. But that's a whole lot more work, especially because we're still, in this case, given what the parameterization was. If we didn't have that, we'd have to go through and find a parameterization for this, and it's just a lot more work. So hopefully you kind of see the benefit of this new method. It's a lot shorter, a lot less involved mathematically to get the answer. But it only works for conservative vector fields.
You have to find that.
Yeah, you would have to be, you have to go back and find this, yep.
How would you even do that? Would you just make?
So this one's just a line. If we went back and found a line from the starting point to the end point, we can find that vector and go through and write a parametric equation for it. But yeah, this R of t there, it is just this. It is not even that curve. It is just a straight line from one to the other. If you wanted to try to parameterize that curve, it'd be tough. You'd probably need some software to be able to go back, and it's not something I'm ever going to ask you guys to do by hand. It's just not. It's not a thing to do. Independence of path is basically the same thing we're just talking about. This isn't really anything new. It's just kind of a different way of talking about it. But if you think about the phrase independence of path, this should make sense. If things are independent, they kind of depend on each other. They operate on their own. And then we're saying the path we're independent of. We don't really care what path you're traveling on. As long as I'm going from endpoint to endpoint, we have this path we're traveling on. So technically, if some vector field is continuous on an open connected region, then a line integral given there is independent path only if the thing is conservative. So they're not really synonyms, but you can basically think about them as saying the same thing. If we know something is conservative, we know it's independent path. If we know it's independent path, we know it's conservative. Different ways of talking about the same thing. Yes, okay, I remember what this one was. All right, so just I'm not going to pay attention to that. It's basically what I just said. Example 5. For the force field given by that whole big function there, show the line integral is independent path, and calculate the work done by F over C from point to point there. So instead of being given the curve, I'm not really told there is some curve there. This is really just reminding us, like we just said, that if we're told something is independent of path, we can show that by showing it's conservative.
So they mean the same thing.
Mm-hmm. So this really isn't any different. It's just a different way of wording the same thing we did there. Again, anytime we're asked to work at line integrals, the first thing you should do is check if it's conservative. Or now we can say check to see if it's independent path. It's the same thing there. So we do have a three-dimensional vector field or a force field here. So it's working with a lot like what we just did. And since we don't have a ton of time left, I'm just going to go ahead and say yes, it is. So I'll say see page 8. Method. But yes, this turns out to be conservative. Okay, if we went through and took the right combination of partials, so partial derivative of p with respect to y makes sure it's equal to the partial derivative of this with respect to z and so on, and check all those, it would work out. Okay, but just to save some time, we'll go through that. You can try to on your own. So we need a potential function. Use that time to do this. Okay. How do we find the potential function?
You find the antiderivative of m, an antiderivative of n, an antiderivative of
And let's be a little more specific. When I find the antiderivative of m, which I have written here, it's going to be dx, dy, dz, d what?
the theta,
Not d theta.
the r,
Nope.
dx, dz, dy,
Just dx. Just that one.
oh, this d, oh yeah, yeah.
Okay. Because we're saying that, we kind of skipped over the conservative part, but this is conservative. It is a gradient of something. So now we're going to undo that gradient process. We're going to work to the original function. So we have the antiderivative that respects x there, which means cosine of y is a constant, and the antiderivative of e dx is just itself. So cosine of y e dx plus some c. And if we do that for all three of those parts there, so negative e dx sine of y with respect to y, what do we get for that one?
Cosine
Negative
or
cosine,
EDX.
negative EX.
You guys are all doing it in different ways, but you're all going to get the same answer. The e dx hangs around, it's a constant. antiderivative sine of y is negative cosine of y, and so the negative eventually cancel out. We get the same thing as the previous one. Okay, but it's kind of interesting to hear the different ways you all think about getting there. And then the last one, antiderivative of 2 with respect to z is 2z. So that means my potential function is what?
It's cosine of y times e to the x.
Plus,
Plus,
technically plus some constant, but really plus that constant is not going to affect anything in our line integral because it's going to cancel out, which I haven't even written.
Function would be f or x, y, z, right?
Yeah, sorry, I should have a z there. Thank you. Yes, that should have said x, y, z. So then we don't really care what shape the curve is. We know it's conservative. We know it's a dependent path. We're just traveling from one point to one point. We're going to go back, and to finish this problem off, we're going to take the potential function at the end point minus the potential function at the starting point. And those, again, just come from what they told us right up here. So a little bit of substitution. This gives us e to the 1 times cosine of pi plus 2 times 3. And if you want to stick your c's in here, go ahead and do it. Just make sure everyone's clear on the fact that they cancel out. Plus c, we don't know what it is there. And we're going to go back and subtract that at the beginning point. So e to the 0 times cosine of pi over 2 plus 2 times 1. And again, that plus c we can stick there. But you can see plus c minus c, those c's just cancel out. So I'm a-okay if you just skip them. I don't need to see that part there. It doesn't really give anything to this. Cosine of pi is -1, so we're going to have negative e plus 6. Cosine of pi over 2 is 0, so that whole thing is just -2. So 4 minus e. Wait a minute, what do I do?
Z is equal, no.
Right, and this is,
No,
and then this is just for that. Okay. We'll end on this one last thing. Consider what happens, and this is just reading the bottom line there. Consider what happens when the object traveling along the path above goes back to its starting point. What's going to happen to this line integral? We got this conservative vector field. We started the point. We travel some path. We end at the same point. What's going to happen? So if the initial point and the end point are the same,
It went back, so it started now.
yeah, so say you've got this vector field that you're traveling through. Come on, Pam.
Vector B0.
Yeah, you start here, you go on some path, you end back over here again. You're just going to do the same thing, last same thing, right? We're just going to get 0, and that's going to be the last we should talk about. But we're out of time for today. So how much work is going to be done in that case, or what's going to be the value of the line integral? We're going to have no work done.
It means you wasted time.
It means you're wasting your time. What it means in a more positive light is that we have another shortcut we can take in just a bit for these guys. Okay, so we'll look at it positively. But yeah, it's basically wasting your time. If you end and start at the same point in this conservative vector field, no work is going to be done. You're basically canceling everything out. You're doing this, you're canceling out, you're getting back nothing. Which is then again makes some problems a little simpler for us. Okay. So we'll finish this up. There's not a whole lot left in this section. We'll finish this up tomorrow. We'll be able to start the last section there, which is, again, still very related material there. The last section is still working at line integrals, traveling around, just kind of some different shortcuts and properties. So try the homework out. It's not super long. If you've got questions, let me know. And if for any reason you guys didn't get your test this time, sorry about that the first time, let me know. But it looks like they at least all sent this time. See you all tomorrow.
All right, thank you. Have a good day.